This research introduces a novel class of electromechanical metamaterials, which enables direct control of total stress reduction through the application of an electric field counteracting mechanical stress. The material combines insulating and conducting materials, allowing for the manipulation of mechanical stress within the bulk material by applying an electric field generated by the conducting material. The authors consider a unit cell consisting of an insulating material cube surrounded by a conducting capacitor in each spatial direction. The electric field between two capacitor plates is assumed to be constant, and the combination of capacitors in each spatial direction ensures that the direction of the resulting electric field can be controlled arbitrarily. The mechanical stress within the bulk material of a single unit cell is also assumed to be constant, enabling stress reduction. The paper formulates a minimization problem to determine the electric field that minimizes the total stress. The stress minimization involves the mechanical stress tensor and the Maxwell stress tensor for linear materials. The total stress is written as the sum of the mechanical stress tensor and the Maxwell stress tensor, resulting in a symmetric tensor. The minimization problem reads as finding the electric field that minimizes the Frobenius norm of the total stress tensor. The necessary condition for the minimization is derived, and the problem is solved by writing the Maxwell stress tensor in index notation using the Einstein summation convention. The derivative of the Maxwell stress tensor with respect to the electric field is calculated, and the resulting equation is simplified to obtain an eigenvalue problem for the mechanical stress tensor. The solution to the eigenvalue problem yields a relation involving the eigenvalues of the mechanical stress tensor, which determines the electric field that minimizes the total stress. The authors also investigate the minimization problem with additional constraints, allowing only tensile or compressive stresses, respectively, and consider the two-dimensional case of plane stress. They discuss their findings and the extent to which the mechanical stress can be reduced. In this paper, the authors focus on the minimization of the electromechanical stress in a dielectric material subjected to an external electric field. The problem is approached by using the Maxwell stress tensor, which represents the stress in the material as a function of the electric field. The goal is to find the optimal electric field that minimizes the total stress in the material. The authors first consider the case of nonpolarizable materials, where the eigenvalues of the Maxwell stress tensor take the form of equation 15. They then calculate the relative stress reduction, as given in equation 19, and use the Karish-Kuhn-Tucker conditions to determine the optimal solution for the electric field. This leads to four possible cases, with the optimal solution being m equals 1/3, 1 plus 2 plus 3, if both inequalities in equation 35 are fulfilled, and m equals 2 otherwise. Next, the authors turn their attention to the case of tensile stress, where the maximum allowed solution is m equals 2 to avoid negative eigenvalues for the total stress. They derive the Lagrangian in equation 40, and find two possible cases for the optimal solution. M equals 1/3, 1 plus 2 3, if m less than 2, and m equals 2 otherwise. Finally, the authors consider the case of compressive stress, assuming that the stress tensor only contains positive eigenvalues. In this scenario, no solution can be found. They provide an example with the stress tensor given in equation 47, and derive the optimal solution as m equals 1/3, 1 plus 2 3, if the inequalities in equation 35 are met, and m equals 2 otherwise. The paper concludes by summarizing the results for the optimal electric field in different scenarios, providing a comprehensive analysis of the electromechanical stress minimization problem in dielectric materials. The research paper presents a comprehensive study on stress minimization in materials under various conditions. The authors consider three cases of compression, where the Lagrangian is formulated to minimize the stress tensor. In the first case, the Lagrangian is defined as the sum of squared differences between the eigenvalues of the stress tensor and a target value, subject to certain inequalities. The solution is obtained by calculating the optimal value of the eigenvalue, which depends on the inequalities holding. In the second case, the Lagrangian is similar, but with a different set of inequalities. The third case involves a different formulation of the Lagrangian, where the eigenvalues are assumed to be positive. The authors then move on to the plane stress problem, where the material is under plane stress and the total stress is zero in all z directions. The Maxwell stress tensor is formulated, and the optimization problem is solved to obtain the optimal eigenvalue. The solution depends on the signs of the eigenvalues, and the authors distinguish between three cases. The paper then presents numerical results for the plane stress case, where the remaining stress is calculated and visualized as a function of the eigenvalues. The results show that the remaining stress is independent of the distance from the origin, but only depends on the angle with respect to the polar axis. The authors introduce polar coordinates to calculate the remaining stress and obtain an analytical solution. The average remaining stress is also computed, and the result is compared to the three-dimensional cases. The authors then evaluate the three-dimensional problems, using spherical coordinates to calculate the relative stress. The results are visualized, showing areas where nearly complete stress reduction is possible, and areas where no solution can be found. The authors solve the problem numerically by randomly creating a sample of uniformly distributed points on the unit sphere. Throughout the paper, the authors use mathematical rigor to derive the solutions, and provide detailed explanations of the methodologies and results. The paper presents a comprehensive study of stress minimization in materials, highlighting the importance of considering the signs of the eigenvalues and the dimensionality of the problem. The results have implications for material science and engineering, where stress minimization is crucial for material performance and reliability. The research paper presents a comprehensive analysis of stress reduction in three-dimensional cases using a novel approach. Figure 4 illustrates the remaining stress depending on the polar angle and azimuthal angle for three-dimensional cases, showcasing three areas with very low remaining stress. The results are presented for unconstrained minimization, minimization of tension, and minimization of compression. The authors calculate the average remaining stress for each case, excluding areas where no solution can be found. The results indicate that a significant stress reduction is possible for most cases, with an average remaining stress of 0.70, 0.66, and 0.87 for unconstrained minimization, minimization of tension, and minimization of compression, respectively. The discussion highlights the limitations of the approach, including the assumption of constant mechanical stress within the unit cell and the potential interference of the electric field from neighboring unit cells. The authors note that a complete absorption of mechanical stress is only possible for rare special cases, but a significant stress reduction is possible for most cases. The paper concludes by suggesting potential applications, such as robotic capsules for endoscopy or drug delivery in medical engineering. The authors emphasize the importance of sensor technology to automate the process and allow for dynamic problems or applications where the material load is not known beforehand. The references provided demonstrate the paper's connection to existing research in metamaterials, negative refractive index, and optical magnetism. The authors draw on a range of sources, including scientific journals and conference proceedings, to support their analysis and conclusions. The paper's methodology is based on a combination of mathematical modeling and numerical simulations. The authors use a uniform distribution to calculate the average remaining stress and exclude areas where no solution can be found. The results are presented in a clear and concise manner, with figures and tables used to illustrate key findings. Overall, the paper presents a novel approach to stress reduction in three-dimensional cases, with potential applications in medical engineering and other fields. The author's use of mathematical modeling and numerical simulations provides a robust framework for analyzing the behavior of metamaterials under different stress conditions. In the realm of transformation optics, researchers have successfully demonstrated the creation of cloaked electromagnetic, acoustic, and quantum amplifiers. 18. This achievement is a testament to the potential for manipulating physical phenomena through innovative materials science. In the context of concrete research, a seminal study by C.D. Johnston in 1968 provided insights into testing concrete in tension and compression. 19. This work laid the foundation for understanding the mechanical properties of this ubiquitous construction material. Dorfman and Ogden's comprehensive treatise on the nonlinear theory of electroelastic and magnetoelastic interactions, published in 2014, offers a deep dive into the complex interplay between electromagnetic fields and mechanical stress in various materials. 20. This seminal work has been instrumental in advancing our understanding of these interactions and their implications for material behavior. Furthermore, the concept of the Maxwell stress tensor for magnetoelastic materials was explored by Ho Man and Chudzika Adamczak in 2009-21. This mathematical construct is crucial for describing the distribution of electromagnetic forces within such materials, shedding light on their unique properties. A recent contribution to the field comes from Blaszczyk and Hackl, who introduced a novel class of electromechanical metamaterials designed to reduce stress through electric fields. 22. This research opens up new avenues for the development of smart materials capable of self-regulation and adaptation. In addition, the generation of random stress tensors, as discussed by Gao and Harrison in 2017, plays a pivotal role in simulating realistic conditions for material testing. 24. This methodology enables researchers to model complex scenarios more accurately, leading to a better understanding of material behavior under various loads. Moreover, the problem of generating uniform random points on the surface of a sphere, addressed by Tashiro in 1977, 23, has far-reaching implications for computational geometry and statistical analysis. The ability to distribute points evenly across a spherical surface facilitates more efficient sampling and simulation techniques in various fields. Lastly, advancements in robotics and drug delivery systems, as outlined by Cortegoso v. et al. In 2021, highlight the potential for innovative technologies to revolutionize healthcare. 26. The development of robotic capsules designed for gastrointestinal drug delivery underscores the interdisciplinary nature of research, where insights from materials science, electromagnetism, and robotics converge to address pressing medical needs.